Right now, if you've ever looked at electrical appliances and so forth, they're measured in watts, right? So power, of course, is a measure of how fast work is done, and so we can write the work divided by the time. Now, work, of course, causes a change or a transfer of energy. So we can write power as the rate of energy transferred divided by the time. All right, so when you use an electrical appliance, what are you doing? You're converting electrical energy into some other form. So suppose you have an electric mixer, right? You want to make a cake, you use your electric mixer to mix the batter together. The electric mixer converts electrical energy into mechanical energy of spinning the beaters, right? An electric motor converts electrical energy into mechanical energy, the spinning of the armature, right? So electrical appliances convert electrical energy into some other form. And the rate that you convert electrical energy into another form is measured in watts. So that's where the wattage rating comes from electrical appliances. All right, now when I was a kid, I used to get yelled at a lot by my mother for leaving lights on, right? Because lights are converting electrical energy into light. And I was notorious for leaving the lights on all the time. My mother paid the bills at our house, and so she would always yell at me for leaving the lights on. In fact, she called our electric bill the light bill. We never called it the electric bill, it was always the light bill. And so I would get the lecture about money doesn't grow on trees and all that. I'm sure that you've heard something similar from your parents when you were a kid, right? Well, how much does it really cost to leave a light on? Well, we can easily figure that out. Now that we know about work and power, we can easily figure that out. So electricity is charged in units of kilowatt hours, which is abbreviated kWh. Well, notice that a kilowatt hour is a unit of energy. So power is energy over time. So power times time is energy. A kilowatt just means 1,000 watts. Prefix kilo means 1,000, and an hour is a unit of time. So a kilowatt hour is 1,000 watts times an hour, or power times time, so it is a unit of energy. So we don't buy power from the electric company, we buy electrical energy, and the unit they charge us is called a kilowatt hour, so that is a unit of energy. Well, how much does it cost to run an electrical appliance? So first, you find the wattage of the appliance, and almost all your appliances will have the wattage rating somewhere on the appliance, usually where the cord comes out. And then divide by 1,000 to convert to kilowatts. So again, a kilowatt is 1,000 watts, so you just take the watts and divide by 1,000 to change it to kilowatts. Then you multiply by the number of hours that it's actually on, and that will give you the number of kilowatt hours that it uses. And then multiply by the cost per kilowatt hour to get the total cost of running that appliance. So it's only using electricity when it's actually on. Okay, I looked at my electric bill, and I know there are taxes and other charges and so forth on there, but I just took the total bill and divided by the number of kilowatt hours that we used. So I could get the cost per kilowatt hour, including all the taxes and extra charges and so forth. And it came out to about 16 cents per kilowatt hour. So it might be a little different in your area. It might be a little higher or a little less. But we're going to use 16 cents per kilowatt hour and then figure out how much it costs to run an appliance. Of course, incandescent light bulbs used to be the standard, but now they're being phased out and being replaced with LED bulbs, which use a lot less electricity to produce light. Well, let's figure out how much it costs for a 60-watt incandescent light bulb to be on for 4 hours. So I take the 60 watts
and I divide by 1,000 to convert it to kilowatts, and I get 0.06 kilowatts. And if it's on for 4 hours, so I have the 0.06 kilowatts times 4 hours, gives me 0.24 kilowatt hours is how much electrical energy it used. And then at a cost of 16 cents per kilowatt hour, I take the 0.24 times $0.16 per kilowatt hour, and I get $0.038, which is about 3.8 cents or less than 4 cents. So if your mother yells at you for leaving the light on, just give her a nickel and tell her to keep the change. I know if I said that to my mother, I'd get in big trouble. Well, of course, you don't just leave one light on. What if you had 10 bulbs? Well, 10 bulbs would be about 38 cents. And 10 bulbs on 4 hours a day for 30 days would only be about $11.52. Now, let's look, what if we replaced our incandescent bulbs with LED bulbs and see how much that costs? So a 60 watt equivalent LED bulb only uses 9 watts. So 9 watts divided by 1,000 gives me 0.009 kilowatts. And then multiply that by 4 hours. We're going to leave the light on for 4 hours, and I get 0.036 kilowatt hours. And at a cost of 16 cents per kilowatt hour, that gives me 0.036 kilowatt hours times $0.16 per kilowatt hour gives me $0.00576, which is a little over half a cent. So it's less than 1 cent. So electric lights are very, very cheap. If I had 10 bulbs, it would only be 5.76 cents, or less than 6 cents. 10 bulbs on 4 hours a day for 30 days is only about $1.73. So electric lights are extremely cheap. So don't worry about leaving that light on. It's really not costing you much at all. Okay, so why is the electric bill so high? Well, let's look at another appliance. How about a refrigerator? Typical refrigerator is about 500 watts, or about 0.5 kilowatts. Of course, it could be a little larger. If you have a much bigger refrigerator, it could be a little larger, but just on average. And of course, your refrigerator doesn't run constantly. It has a compressor motor and it has a thermostat. So once it cools off inside, the compressor motor turns off and it's no longer drawing electricity. So it only actually running when the compressor motor is running. And so it really doesn't run that often. Now suppose we're opening and closing the door a lot. We're in and out of that refrigerator a lot, and we'll take an estimate that it's running 15 hours a day. That's probably a pretty high estimate. Well, 15 hours per day at 500 watts, that gives us 7.5 kilowatt hours per day. And if the cost is 16 cents per kilowatt hour, we take the 7.5 kilowatt hours times 16 cents per kilowatt hour, gives us a cost of about $1.20 per day for the refrigerator. And it's actually probably less than that if you're not opening and closing the door a lot. Well, to me, $1.20 a day, it's worth that just to keep my beer cold. So again, why is the electric bill so high? It's not the refrigerator. Well, let's look at central air conditioning. Central air conditioning is about 5,000 watts or 5 kilowatts. Now, if you have a bigger house, it might be a little bigger than that, or if you just have a small apartment, it could be less. And let's say our house is not insulated very well and the summer is really, really hot, so that air conditioner is running 15 hours a day. Again, like the refrigerator, your central AC is controlled by a thermostat. And once it cools off inside, the AC turns off. So we only need to use electricity when it's actually running. But again, we'll take a high estimate of 15 hours a day, and we'll do it for a 30-day month. So 5 kilowatts times 15 hours a day times a 30-day month gives us 2,250 kilowatt hours per month. And then at a cost of 16 cents per kilowatt hour times the 2,250 kilowatt hours, that gives us $360 per month. So this is why the electric bill is so high. It's not because you forgot to turn the light off. So it's that central air conditioning is using almost all the electricity. Okay, so appliances that use electricity to produce heat usually cost the most. So for example, electric ranges, electric clothes dryers, electric water heaters, electric room heaters. These are all in the thousands of watts. Electric range is usually about 6,000 watts. An electric clothes dryer is also about 6,000 watts or 6 kilowatts. So if you have a big family and you're doing lots of laundry and have that clothes dryer running most of the day, the number of kilowatt hours can add up pretty quickly. Same thing with electric range. If you're doing a lot of cooking and baking in a day and you have that electric range on for a long time, that can use up a significant number of kilowatt hours as well. Hair dryers, irons, coffee makers, these are all in the thousands of watts. Hair dryer, handheld hair dryer is usually around 1,400 watts or 1.4 kilowatts. But we don't have those on for long periods of time. And so the total number of kilowatt hours used is still going to be pretty small because we don't have it on for a long time. So the thing to remember, though, is that a kilowatt hour is a unit of energy. So we are buying energy from the electric utility company. We're not buying power. We're buying energy, and the unit is a kilowatt hour. All right, let's look at one more power example. We have a 6.5 kilogram crate is lifted by a man pulling on a light rope that passes through a single pulley attached to the ceiling. If the crate is lifted at a constant speed of 2.2 meters per second, what is the power delivered by the man? Now, part B, what if he lifts the crate at a constant acceleration from rest to a height of 1.5 meters in 0.55 seconds? What is the power delivered by the man now? All right, so we'll do part A first, and then we'll look at part B. All right, so part A, we're lifting the crate at a constant speed. So constant speed means there's no acceleration. So the force pulled on the rope by the man is equal to the weight of the crate. So then the force is just the weight, mg, and then times the speed, 2.2 meters per second. So we got the 6.5 kilograms times 9.8 meters per second squared for g times the 2.2 meters per second, and that gives us 140 watts rounded to two significant digits. All right, so next we'll look at part B. Now part B says the crate is lifted at a constant acceleration from rest to a height of 1.5 meters in 0.55 seconds. What is the power delivered by the man? All right, so if he's pulling the rope and we're accelerating, then that means the force that he's pulling is greater than the weight of the crate. So we can't just take the weight of the crate. We need the force supplied by the man. Well, how can we find that? Well, we can write the force as the mass times the acceleration. And we're accelerating from rest to a height of 1.5 meters in 0.55 seconds. So we can use the kinematic equations that we developed in the beginning to find the acceleration. Well, if we're accelerating from rest, the change in the height is just 1/2 the acceleration times the time squared, or 1/2 delta t squared. Solving for the acceleration, we get 2 times the height, delta y, over the time squared, delta t squared, is the acceleration. So then the force is the mass times the acceleration, and then for the power, we multiply the force times delta y over delta t. So we've got 6.5 kilograms for the mass, and then we have the 2, and then we have a delta y squared in the numerator, so that's 1.5 meters squared, and then in the denominator we've got a delta t cubed. So we take the 0.55 seconds and cube that. And when I crunch those numbers, I get 175.8. Rounded to two significant figures, it's 180 watts. All right, so that's the end of the power examples that I'm going to do. In the next video, we'll move on and we'll look at conservative forces in potential energy and energy conservation. Hi, Dr. C here. I want to ask you to please help support this channel. There are a number of links in the video description to Amazon.com. If you purchase any items from Amazon by entering through these links, even if it's not one of the items listed, I will receive a small commission that helps to produce more content. There is no additional cost to you whatsoever. Also, please leave your comments, questions, or suggestions below. I want to thank you for support of this channel and please subscribe. I hope you find my videos useful.